Hello everyone and welcome back. Over the last 2 to 3 sessions, we have built our foundation. We learned the open channel flows is all about the free surface, and we discovered that the Froude number, the ratio of the flow velocity to the wave speed, dictates entirely the personality of the flow. Then we derived that the wave speed itself is c is equal to under root gy, and so how it governs whether a flow is subcritical or supercritical. But here is the thing: rivers meander, the streams have riffles and pools. Nature is messy. However, when we design a channel, an irrigation canal, a stormwater drainage ditch, a sewer line, we want predictability. We want a channel that does its job consistently over its entire length. That brings us to the topic for today, which is the uniform depth channel flow. This is the engineer's ideal. It is a flow where the depth, velocity, and cross section do not change along the channel. We denote this by saying that dy over d of x must be equal to 0. So think of a perfectly constructed prismatic canal carrying water at a constant depth for miles. So this is the foundation of open channel design. So how is uniform flow physically possible? If a if the water is moving at a constant velocity, there is no acceleration. From Newton's first law, that means the net force on the water must be zero. Let us look at these forces. And we take a control volume of the length L in our uniform channel. These are two main forces in the direction of the flow. One is the driving force and the other one is the resisting force. The first driving force is the component of the fluid's weight that is pulling it downhill. If the channel has a small bottom slope S naught, the weight component down the slope is W sine of theta component, which for small slopes is approximately W times S naught, where we assume that the sine of theta is approximately equal to theta. The second one is a resisting force. This is a shear stress tau W exerted by the channel walls and bottom on the fluid acting up the slope. So this shear stress acts over the entire wetted perimeter P over the length L. So the total resisting force is tau W multiplied by the wetted perimeter P multiplied by the length L. So for no acceleration, these forces must balance. But wait, are not there all pressure forces? There are at the upstream and downstream ends of our control volume, but because the flow is uniform, the depth is the same at both the ends. And since the pressure is hydrostatic, the pressure force pushing on the upstream and end is exactly equal to the pressure force that is pushing on the downstream end. They cancel each other out perfectly. So our force balance simplifies beautifully. We can write the mathematical equation as listed over here. So where A is the cross-sectional area and volume is area times length L, and the weight is gamma times area times the length L. So we can cancel the length L and rearrange it. Let us introduce a new critical parameter, which is the hydraulic radius RH, which is defined as the cross-sectional area divided by the wetted perimeter. RH equals to area over the perimeter. We have already studied in the previous sections of this particular lecture. So this gives us a fundamental relationship for the wall shear stress in the uniform flow. Now this particular equation, tau W equals to gamma RH S naught, is very powerful. It tells us that the shear stress on the channel boundaries is directly proportional to the hydraulic radius and the slope. So a steeper slope or larger hydraulic radius means more shear stress. Now This particular equation is very nice, but it contains a TW, which is a wall shear stress, which is difficult to measure directly. We want an equation for the velocity V now. We need a way to relate the shear stress to the velocity. So this is where we enter the realm of empirical engineering. For most open channel flows, the Reynolds number is very huge. It's turbulent flow. And for the highly turbulent flow over a rough surface, we know from the pipe flow course that the wall shear stress is proportional to the dynamic pressure, rho v square over 2, and is independent of the viscosity term. So it depends only on the roughness, which we seen as epsilon. So we can say that tau w equals to k times the dynamic pressure term, which is rho v square by 2. Here k is the constant related to roughness. So substituting this into our force balance and simplifying it, we can have the final relationship as v is equal to c under root rh times s naught. So we can lump all the constants into one big constant c, and we get the Chezy equation over here, one of the oldest in the fluid mechanics, dating it back to 1768. So this was a great start, but over the century later, engineers found the dependence on the hydraulic radius was not quite right. Through extensive experiments, they found that the velocity was a better correlated with RH hydraulic radius raised to the power 2 by 3 rather than the hydraulic radius raised to the power 1 by 2. So this confusion led to the equation that is still used worldwide today, which is the Manning equation, developed by the Robert Manning in 1889, which is given over here by in this particular equation, which is V is equal to hydraulic radius raised to the power 2 by 3 multiplied by the slope under root of the slope divided by the n. Here n is the Manning resistance coefficient, and it is an empirical parameter that represents the roughness of the channel surface. So now I need to stress something very important over here, that this particular equation is not dimensionally consistent in its basic form. The coefficient n has the units, and in SI units we use the equation as written, but in British gravitational BG units we have to add a conversion factor, which is the kappa k, and its value we assume as k is equal to 1.49, because the foot is not a nice round multiple of the meter. So the form you will use is given by these two equations, which is represented over here. V is equal to kappa over small n, hydraulic radius raised to the power 2 by 3 times the slope under root of the slope. And the second equation is related to the volume flow rate, which is equal to kappa over n, area times hydraulic radius raised to the power 2 by 3 multiplied by the under root of the slope s naught. So where k, which is kappa, is equal to 1 in the SI units, but it has the value of 1.49 in the BG units. Now this brings us to $1 million question: what value of the n do we use? This is where engineering judgment means tabulated data meets its tabulated data. As we can see over this particular slide, that this is a table. It's a fascinating list. You will see everything from natural channels. A clean and straight natural channel has an n value of about zero point zero 0.03. A sluggish stream with deep pools is rougher, so n is higher, around zero point zero 0.04 value. A flood plain with heavy brush, that has an n value of 0.075, and a flood plain with trees, uh, that can be as high as 0.15. So then look at the man-made or artificially lined channels. The glass is incredibly smooth and has the value of zero point zero 0.01. Finished concrete has the value of 0.012. Unfinished concrete has an 0.014, and whereas the rubble masonry has the value of 0.025. So we conclude that the rougher the surface, the higher the value of the Manning's coefficient n. And because the Q, the volume flow rate, is inversely proportional to the Manning's coefficient n in the Manning's equation, a 10% error in the estimating n could lead directly to a 10% error in your calculated flow rate. So choosing the right n value is one of the most critical steps in the open channel design. Now, let us see this in action with an example problem. I want to highlight a couple of them to show how you could use the Manning equation. So, in this particular example, we have a trapezoidal canal lined with finished concrete. We know the geometry, we know the slope is 1.4 feet per 1,000 feet, and we know the depth is 5 feet. We want the flow rate. So this is a straightforward calculation. We compute the area A from a trapezoidal geometry. We compute the weighted parameter P. Then we get the hydraulic radius as RH equals to the area over perimeter, which comes out to be 3.25 feet. And then we look up for the n for finished concrete in the table that we have just saw. So we plug it all in the relevant equation, and with the kappa value of 1.49, since the problem is in the British gravitational units, so here kappa we use is of the 1.49 value. So that's the massive flow rate that we are getting over here is 915 cubic feet per second. So that's the massive flow rate for a slope of only about 0.0014, which is less than a tenth of a degree. And notice that they also calculate the Froude number as 0.804, and which also dictates that the flow is subcritical in this region. So this is typical for such canals. Now, moving towards the another example problem, which states that we now know the flow rate as 10 meter cube per second and the slope, but we don't know the depth. The channel is VD, and so the value of the n is equals to zero point zero 0.03 from the table. Now we have a problem. Our equation for A and the hydraulic radius RH are both functions of the uniform of the unknown depth y. If you plug them into the Manning equation, you get a highly nonlinear equation. So this is a classic case for trial and error and or a root finding numerical method. So what would be its solution? That you have to find uh, y through hit and trial calculation, and we can find easily the y value of 1.5 meter over here. This is called as a normal depth for this flow rate. It's the depth at which the channel will carry this flow uniformly. So your home task is to solve this and through hit and trial method, and find out the suitable y value. I found out its value as y equals to 1.5 meter. So give it a try by solving it. Another example problem is a very fascinating one. They ask that in a circular pipe flowing partially full, at what depth does the maximum flow rate occurs? Intuitively, you might think it's when a pipe is full, but look at this particular figure. The graph of Q versus the depth shows that the maximum flow rate actually occurs when the pipe is about 93.8% full, which is also given by a relationship that y is equal to 0.938 times the diameter. So at full pipe, the flow rate is only 92.9% of that maximum. Why? Because when you get very close to the top, the small increase in the area you gain by filling the pipe a tiny bit more is offset by a large increase in the wetted parameter, which increases the friction. More resistance for very little gain. This is a non-intuitive but crucial result for designing storm sievers. Now, what happens when your channel is not made up of one material? A common situation is a drainage canal, which with a concrete bottom for strength and gravelly sides of erosion control for erosion control, or a river with a main channel and a wooded plain. So the roughness varies around the wetted parameter. So this particular example shows how to handle this. The key idea is to divide the cross section into subsections, each with its own value of the n, its own area ai, and its own wetted parameter pi. So imaginary vertical lines between the sections are not counted in the wetted parameter. Only the solid boundaries we will be count here. We then calculate the flow rate for each subsection using the Manning equation and then simply add them up as Q is equal to the sum of the Q1 plus Q2 plus Q3. So in this particular example, the main channel is smoother than the VD sides. When they do the full calculation, when we calculate the full calculation, we would get the Q around about the value of 16.8 cubic feet per second. If you try to treat the whole thing as one big channel, you would have to calculate an effective value of n that gives the same value of the volume flow rate Q. Then find that effective n is about 0.018, which is in between the smooth channel value and the VD side value. So this makes perfect physical sense. Finally, let us talk about optimization. If you are designing a channel, if you want to move a given flow rate Q with a given slope S naught and a given lining material also, which is hereby specified as the value of N. So, but you have a choice. What shape should the channel be? A wide or a shallow one, a deep or a narrow one? So these three questions are of paramount importance. So if you look back at the Manning equation, you can rearrange it to solve for area as this particular equation. So for a given q, s naught and n, the term in the brackets is constant. So to minimize the cross-sectional area A and thus to minimize the excavation and lining costs, you must minimize the wetted parameter P. The shape with the smallest wetted parameter for a given area is a semicircle, but we often use simpler shapes to build. So for practical shapes, we ask what are the optimal proportions. For a rectangle case, the best hydraulic section occurs when the depth is half the width, or B over Y ratio is equal to 2. But for a trapezoidal section with 60-degree sides, it's a specific proportion. And also for a triangle, it's a 90-degree triangle. So this is shown in the this particular figure and derived from the example problem. And it is a beautiful example of using a simple equation to derive an optimal cost saving design. So today we have covered the workhorse of open channel hydraulics, which is a uniform flow. We have seen that it represents a perfect balance between gravity and friction. We have also introduced the Manning equation, which lets us calculate the velocity and the flow rate for a given channel. We have also learned how to handle composite roughness and even how to optimize the channel's shape for maximum efficiency. But here is the catch, that the uniform flow is an ideal scenario. In the real world, channels change their slope. They have obstructions also, and they have to transition from one condition to another also. So in those cases, the depth is not constant. So what happens when the driving force of gravity and the resisting force of friction are not in the balance? That's when the depth changes along the channel. That brings us to our next topic, which is related to gradually varied flow. We will use the concepts we have built in this particular lecture, which is about the Manning's equation, the force balance, to analyze how water surfaces rise and fall and as they move downstream. And we will also classify the different types of profiles that can occur. So for now, I want you to appreciate that the simple looking Manning's equation is one of the most powerful and widely used tools in civil and environmental engineering. It is the key to designing the canals that irrigate our crops, the drainage ditches that protect our roads, and the sewers that serve our cities. So, see you next time in the next section. Thank you.